Hello everyone, and welcome to the Chem Videos Sunday night live stream. Tonight, we are going to continue our discussion on acids and bases that we started a week ago. By the way, if you missed that stream, I'm going to be compiling all of my acids and bases live streams into a playlist cleverly titled Acids and Bases Live Streams. So by the time this video gets uploaded, I'm going to compile those together and they will be in the link. There will be a link in the description of the video. So, without further ado, let's go ahead and get into Acids and Bases Volume 2. Here we go. So, just a little bit of an announcement. I kind of always make this announcement, but if you would like to contribute to the discussion, you are highly encouraged to do so. Your feedback is always welcome, highly appreciated. So if you'd like to leave your thoughts in the chat, if you're watching this live, feel free to do so, or even better, you can call into the show via Discord. There's a link down there in the description for you to call in if you are interested. Okay, Acids and Bases Volume 2. So I'm going to start by just giving a brief review of the last stream that we did a week ago. That was Acids and Bases Volume 1. And so we started that discussion off by, I basically gave a short disclaimer about chemical equilibrium. What I said was that chemical equilibrium is kind of a prerequisite for understanding acids and bases. If you don't have a solid understanding of equilibrium, you don't have much of a chance of understanding acids and bases. So if you don't understand chemical equilibrium, fear not, because I do have an entire playlist on it that I recently recorded called Chemical Equilibrium Live Streams. And of course, there will be a link to that in the description as well. So we talked about that little chemical equilibrium disclaimer. We also talked about some general characteristics of acids and bases. For instance, acids tend to taste sour. Some of them can dissolve some metals. They tend to turn blue litmus paper red, and they tend to neutralize bases. And then on the other side, you have bases, which taste very bitter, feel kind of slippery, like this soap over here. They turn red litmus paper blue, and they tend to neutralize acids. In addition to the characteristics, we also talked about some common acids and bases like hydrochloric acid, acetic acid. Those are a couple of very common acids. And then we talked about common bases like sodium hydroxide, sodium bicarbonate. And we talked about some of the things that they're used for. And then for the bulk of the discussion, we talked about the definitions of acids and bases. As confusing as it may sound, there is more than one definition of acids and bases. It depends on what situation you're talking about, which definition is most convenient used. The three definitions of acids and bases, of course, are the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. And in last week's live stream, we talked about Arrhenius and Bronsted-Lowry definitions, and we're going to save the Lewis definition for later. So just going briefly over the Arrhenius definition, according to the Arrhenius definition of acids and bases, an acid is a substance that produces H+ ions in aqueous solution. So if you have, for instance, HCl, hydrogen chloride, if you throw that in water, it'll produce H+ and Cl- according to this equation down here. And I'm going to resize myself and move myself so that we can see everything that's going on here. There we go. Sometimes I forget to do that, but I'm glad I remembered this time. Anyway, so because HCl produces H+ when you put it in solution, HCl is therefore an Arrhenius acid. And then you have bases, which according to the Arrhenius definition produce hydroxide ions, OH-, when they are put in aqueous solution. So a classic example of an Arrhenius base would be sodium hydroxide, because when you throw it in water, it produces sodium ions and hydroxide ions, according to this equation down here. I'm not sure if you guys can even see my mouse cursor. I'm trying to point to things, but I'm not even sure if you guys can see my mouse cursor. Anyway, on the bottom right of your screen, that's the equation that describes what happens when you put sodium hydroxide in water. So because sodium hydroxide produces OH- in water, it is therefore an Arrhenius base. So the Arrhenius definitions of acids and bases is pretty straightforward. One thing that I really tried to emphasize a week ago, and I'm going to re-emphasize right now because it's so important, is that anytime you have an H+ ion, so if I go back a slide, I'm going to move myself again, make myself a little bit bigger. How do I do that? Go. Whoops. I am trying to make myself bigger. There I go. Streaming software. Having a hard time with it sometimes. Anyway, So if I go to the previous slide, we saw that, oh look, now I'm in the way again. So an Arrhenius acid produces H pluses in solution. So like this HCl, right? It produces H pluses in an aqueous solution. But one important thing to understand about H plus ions, which are basically just protons, right? Because a hydrogen atom has a proton and an electron. Take away the electron, you're left with an H plus, which is just a proton, right? So protons, when they are in water, they are very, very reactive, and they will react with a water molecule to form this species here called the hydronium ion, H3O+. Very, very, very important polyatomic ion, and it's very, very important to understand that when you see the terms H plus and H3O+ in the context of acids and bases, they can be used interchangeably. They mean the same thing. So everybody who is experienced with chemistry understands that anytime you have a proton in water, it will bind to a water molecule to form a hydronium ion. So now that we all understand that, we can move forward. So I'm going to move myself again. I am constantly in the way. I need to figure out how to format these slides better so that I'm not always in the way. Anyway, so that was the Arrhenius definition. Pretty straightforward, nothing too crazy there. Then we switched gears and talked about the Bronsted-Lowry definition of acids and bases. And the Bronsted-Lowry definition, if you recall, instead of describing what the compound produces when you put it in water, it's talking about how that compound behaves in the event of an acid-base reaction. So according to the Bronsted-Lowry definition, an acid is something that donates a proton, it donates an H plus in the event of an acid-base reaction, and a base is something that accepts an H plus in the event of an acid-base reaction. It's like, thank you for that H plus. That's a base, right? So a good example of an acid-base reaction is the one shown down here, where we have HCl with water, reacting with water to produce H3O plus, the hydronium ion, and Cl minus. So the HCl is acting as the Bronsted-Lowry acid because it's donating a proton, and the water in this case is acting as the Bronsted-Lowry base because it is accepting the proton from the HCl. And of course the products are the result of that transfer of H plus from the acid HCl to the base water. Okay, so acid, proton donor, base, proton acceptor, according to the Bronsted-Lowry definition. And another example that we saw of an acid-base reaction is this one here, where we have NH3, that's ammonia, which actually is a base, and this time it's acting as a base, it's accepting a proton from water, which in this reaction, water is acting as an acid. And that, of course, produces the ammonium ion, that's NH4+, and the hydroxide ion, OH-. And so notice here that under the Bronsted-Lowry definition, it kind of expands the list of substances that can become bases, right? Because remember, the Arrhenius acid, it had to produce hydroxide ions in solution in order to be considered a base. Well, notice that NH3 is a Bronsted-Lowry base, but it doesn't actually have any hydroxide ions in it. You don't actually have to have any OH minuses in the compound for it to be considered a base. Why? Because all that it needs to do to be considered a base, according to the Bronsted-Lowry definition, is to accept a proton from an acid. And the other thing that should be abundantly clear at this point is that in the previous reaction, water was acting as a base, and in this reaction, water is acting as an acid. So water, it's like a switch hitter, right? Water can go both ways depending on what you put with it, right? It can act as an acid or it can act as a base. And there's a name for substances like that that can act as an acid or a base, and I'll leave it to you. You can type a message in the chat if you can remind me what that term is, that term that describes substances that can act both as an acid and as a base. I am waiting on you guys. Somebody, I know you guys know it, somebody at least does, drop that in the chat, and because I always try to stimulate and encourage your participation whenever I can. All right, so the last thing that we talked about a week ago, as I move myself over here to the top right-hand corner, out of the way once again, is the concept of conjugate acid-base pairs. So remember, a conjugate acid-base pair is simply two substances that are related to one another by the transfer of a proton. So in this case, the conjugate acid-base pairs are shown in the same color. So in that HCl water reaction, HCl, of course, that's the acid, water is the base. The conjugate acid of HCl is the the conjugate base of HCl is the Cl minus. The conjugate base is basically the substance that remains after the acid has donated its proton away, right? If you have HCl and you lose an H plus, you end up with a Cl minus, and therefore HCl and Cl minus are a conjugate acid-base pair. Cl minus is the conjugate base of HCl. A lot of chemistry jargon in there. It's very important that we get our heads around it and that we understand it. And then, of course, you have water, which in this reaction is acting as the base, and H3O plus, the hydronium ion, that's the conjugate acid of water. And then here down below, the other reaction with ammonia and water. Ammonia is the base, water in this case is the acid, and then the conjugate acid of the base ammonia is NH4 plus. It's basically the substance that results when the ammonia, the base, has accepted a proton from the acid. And then over here you have the conjugate base of water, which is the hydroxide ion, OH minus, the base that's left over once that acid, in this case water, has donated its proton away. So that is everything that we talked about last week. It was a very gentle introduction to acids and bases, and today we're going to get a little bit more technical. So if you guys are ready, let's do it. So the content of this video, what are we going to talk about? Well, we're going to talk about the concept of acid strength. So acid strength. And acids are broadly categorized into two categories called strong acids and weak acids. And the difference between strong acids and weak acids is the degree to which the acid dissociates or ionizes when you put it in water. So a strong acid is something that completely ionizes in solution. So the general form of a chemical equation in which you're dealing with a strong acid is going to look like this equation up above, where you have HA, that's just the generic formula for just a generic acid, HA, reacting with water to produce hydronium ion and the conjugate base of that acid HA. And notice that the reactants and products are separated by a single arrow pointing from left to right. So you guys know what that means, that single arrow pointing from left to right? I hope you do. We've talked about it before. That single arrow represents a complete conversion from reactants to products. It means your reactants react together, and once they're gone, they're gone. Products are there to stay. They are not going to react with one another to form the reactants in any significant way. It is a complete ionization, a complete dissociation, right? And then you have weak acids, which only partially ionize. They only partially dissociate in solution. And so notice that the chemical equation, the general form of the chemical equation with a weak acid reacting with water, looks the same as it does with the strong acid. The only difference is the symbol that is placed between the reactants and products. In the case of a weak acid, what we're looking at are these two half-headed arrows, and if you've been following my channel, we talked about chemical equilibrium recently, then we would understand that those two half-headed arrows represent an equilibrium process, a dynamic equilibrium in which products are becoming reactants and reactants are also reacting with one another to form products. And equilibria kind of range all over the place in terms of the extent of the reaction, how much of those reactants have become products at any given time, characterized by something called an equilibrium constant. And I don't want to reteach equilibrium. If you need help with that, like I said, I have an entire playlist called Chemical Equilibrium live streams. So acid strength, two categories: strong acids, weak acids. Strong acids dissociate completely. Weak acids ionize only partially. So that is what's going on with strong and weak acids. So let's look at a few common strong acids just so that we can sort of understand, we can identify a few acids that are strong and a few acids that are weak. So hydrochloric acid, HCl, that's kind of the most common example of a strong acid. Hydrobromic acid, HBr, hydroiodic acid, HI, nitric acid, HNO3, very, very common strong acid. Perchloric acid, that's another one, that's HClO4. Sulfuric acid, H2SO4, all 6 of these acids and many, many more are considered strong acids. They ionize completely when you put them in water, and therefore all of these acids would, in the case of all 6 of these acids, this formula below, where you have the acid reacting with water to form hydronium ion and the conjugate base of the acid, separated by a single arrow pointing from left to right, indicating a complete reaction. That general formula would apply to all of the acids that are listed on the screen here. Those are some common strong acids. Let's look at some common weak acids. Hydrofluoric acid. HF is a weak acid. And it's kind of counterintuitive because HF is really, really, really corrosive, really gnarly stuff. It'll actually dissolve glass. It'll eat through glass. But just because it's really, really corrosive and really dangerous doesn't mean that it's necessarily a strong acid. So you could think of it the other way. Just because it's considered a weak acid, just because it doesn't ionize completely, doesn't mean that it's not very, very dangerous. So hydrofluoric acid is one. A week ago, I was talking about it. It's used for glass etching and things like that. Acetic acid, very, very common weak acid. That's HC2H3O2, the main component of vinegar. You can find it pretty much in any chemistry lab. Formic acid, HCHO2. Sulfurous acid, H2SO3, not to be confused with sulfuric acid, which is H2SO4, is a weak acid. Carbonic acid, H2CO3. Phosphoric acid, H3PO4. These are all examples of weak acids, and therefore this formula down here where we have the equilibrium arrows separating the reactants and products, that formula or that chemical equation, that general form of the chemical equation would apply in the case of all 6 of these weak acids. So it's important to understand that acid strength, I'm going to move myself down here and make myself just a little bit bigger. There we go, maybe a lot bigger. All right, so it's important to understand that even though we use these 2 categories, strong and weak, to categorize these acids, it's important to understand that acid strength is a continuum. It's like a big spectrum that kind of goes all over the place. And there are some acids that are very, very kind of on the blurry line between those 2 categories. That doesn't mean that the categories strong and weak are useless or invalid. And the analogy that I like to use when it comes to these continuum thought experiments is to, we all know the terms puddle, pond, and lake, right? Puddle, pond, lake. All 3 of those terms describe what? Well, they describe the size of a body of water. Now, I couldn't tell you the exact moment a puddle becomes a pond or a pond becomes a lake. Like, for instance, how big must a puddle be so that one more drop of water will turn that puddle into a pond? I don't know. How big should a pond be such that one more drop of water turns that pond into a lake? I don't know. Like the lines between the categories tend to get a little bit blurry or a little bit imprecise. Nonetheless, the categories puddle, pond, and lake are still useful, and they're not invalid. They're useful in describing the size of a body of water. So that's how we need to think about acid strength. It's not rigid categories, strong and weak, although having those 2 categories to describe the level or degree of dissociation or ionization is still a very, very useful concept. So, okay, now that we understand that acid strength is a continuum, let us go ahead and move on. By the way, if you're enjoying this stream, if you're finding it valuable, if you're finding it helpful, I would certainly appreciate you leaving a thumbs up on it. It really helps to go a long way for discoverability. And if you're feeling super generous, consider sending a super chat. I would be honored to receive it. I'm also doing sulfur hexafluoride shout out, so if you want to send a super chat and you want to hear me say something in a really, really deep, creepy sulfur hexafluoride voice, I would be happy to oblige. So, all right, let's continue. So let's talk about, so we talked about the category strong and weak acids. We talked about what they mean. We looked at a few common examples of strong and weak acids. But let's talk about why some acids are strong and some acids are weak. In other words, what is the origin of acid strength? Well, the origin of acid strength, the reason why some acids are strong and some acids are weak, the phenomenon that's responsible for determining how strong an acid is, it's all about the attractive force between the conjugate base of the acid and H plus or H3O plus. Remember, H plus and H3O plus, they can be used interchangeably. So if you have a strong acid, the reason why that acid is strong is because the interaction, the attractive force between the conjugate base of that acid and H plus is very, very weak. Because that attractive force between the products, in this case, the conjugate base and H plus, because that attractive force is so weak, they're much less likely to react together to form the reactants. In other words, the reverse reaction of the chemical equation is much, much less likely to occur because it's such a weak attractive force. On the other hand, if you have a weak acid, well, now we have a strong attractive force between the conjugate base and H plus. And if there's a strong attractive force, that means they're going to react together to form the reactants. The reverse reaction is going to take place. It is going to happen to a significant degree that will result in not a complete ionization, which happens with strong acids, but a partial ionization. So hopefully that sheds a little bit of light on why some acids are stronger than others. So now we can move on. So let's talk about how we can quantify the strength of a weak acid. We know that weak acids are stronger, or excuse me, we know that weak acids are weaker than strong acids. But what if there was a way by which we can quantify the strength of a weak acid, and maybe we could compare the relative strengths of a few weak acids? In other words, we have a few weak acids. We want to know which one's the strongest weak acid. We want to know which one's the weakest weak acid. Wouldn't it be great if there was a way to quantify such a relationship? Well, lucky for us, there is, and it's called the acid ionization constant, also called the acid dissociation constant, and it has the symbol capital K sub A. Capital K. That looks kind of familiar, doesn't it? Yeah, it does. Where have we seen a capital K before as a symbol in chemistry? What property have we seen capital K describe in our general chemistry classes? Well, that would be an equilibrium constant, right? So it's nothing more than an equilibrium constant. So the way that we quantify the strength of a weak acid is we use equilibrium constant. So for instance, if you have a weak acid in water, right, you're going to have this formula here where you have HA, that's just the general formula for the acid, reacting with water to produce hydronium ion and the conjugate base A minus, and you got those equilibrium arrows. So what would be the equilibrium constant expression for this reaction? Well, if you remember, when we were studying equilibrium, we looked at something called the law of mass action, which states that the equilibrium constant expression is simply going to be the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. Now, in this equation, all of the stoichiometric coefficients are 1, so we don't have to worry about raising it to any power other than 1, which basically just means leaving it alone, right? Because anything to the first power is just whatever it is, right? So we don't have to worry about that. So the expression for the acid ionization constant of a weak acid is going to look like this, where we have concentration of H3O plus times concentration of A minus, that's the conjugate base, that whole thing divided by the concentration of the acid, HA. Now you might be asking yourself, well, what about the water? Why isn't the water in the denominator of this equilibrium constant expression? Well, this is a heterogeneous equilibrium, right? Pure solids and pure liquids do not belong in the expression for an equilibrium constant. Why don't they belong? Why don't we include them in the expression? Well, because pure solids and pure liquids do not change their concentrations as the reaction proceeds in one direction or another. The concentration of pure liquid water depends on its density. It does not depend on how much of it has reacted. So that's why we omit the water from the equilibrium constant expression. And so therefore, this expression is what results. Concentration of hydronium ion times concentration of that conjugate base A minus divided by concentration of our acid HA. Anybody has any questions? Now would be the time to ask them. I would love to answer them because we are going to move on. Okay, so just so that you guys can get a little bit more of an intuitive understanding of the acid ionization constant, K sub A, I've pulled this off the internet. This is just a list of a few weak acids and what their corresponding Ka values are. Notice that they're kind of all over the place. You have down here all the way at the bottom, you have trichloroacetic acid, which for a weak acid is actually pretty strong with a Ka value of 2.2 times 10 to the minus 1. The larger the Ka value, the stronger the acid, as I'm sure you have probably already figured out. But then again, you have all the way up here, you have hydrocyanic acid, 6.2 times 10 to the minus 10, which is a very, very, very small number. So that would be a very, very weak acid. So of these weak acids, hydrocyanic acid is among the weakest of the weak in terms of these weak acids. Now, I don't want you to waste your time trying to remember the Ka values of every individual acid. One thing that I also need to point out is that the acid ionization constant, just like any equilibrium constant, depends on temperature. So I'm assuming that usually the temperature that will be reported in your general chemistry textbook is 25 degrees Celsius or 298 kelvins. So I think all of these Kas are for 25 degrees C. I'm not 100% sure of that, but I think that's what's going on here. So I just wanted to make sure I got that in there. But yeah, these numbers are really all over the place. So it would be nice if there was some type of scale that really kept these numbers in check so that they weren't all over the place. And lucky for us, there is a scale like that. It's called the pH scale. We're not going to talk about it yet, but we're definitely going to talk about it starting next week and beyond. So I just, like I said, I don't want you to memorize Ka values for all these acids. I just kind of want you to understand that some weak acids are much, much stronger than other weak acids. So with that understood, we can go ahead and move on. So now we're going to talk about another concept, which is called the autoionization of water. Now, if you understand the root word auto, you probably understand what the autoionization of water refers to. But to understand this concept, we need to remember something about water. This is something that I talked about last week, and this is also something that I touched on earlier tonight, is that water can act as either an acid or a base. So in the HCl in water example, water acts as a base, accepting a proton from HCl. And in the ammonia NH3 example, we have water acting as an acid, donating a proton to the base NH3. So H2O, water, can act as an acid or a base. It is amphoteric. That's the term I was looking for earlier. Amphoteric refers to substances that can act as either an acid or a base, right? So the question on my mind, and hopefully this question is on your mind too. I would love to hear what your thoughts are if anybody actually wants to type any messages in the chat. It's been a very slow stream for the chat so far. I haven't seen any messages at all. Usually somebody types at least something, but I guess everybody's just listening, so that's cool too. So the question on my mind is, can water act as an acid and a base at the same time? In other words, if you have like a glass of water, right, can one water molecule react with another water molecule? In other words, can one water molecule donate a proton to another water molecule to result in hydronium ion and hydroxide ion? So what do you guys think? Can water act as an acid and a base at the same time? Not a rhetorical question. I really want somebody to answer it, but I'm not going to wait super long for anybody to answer it. Oh, we have an answer in the chat from Christopher Demeralt. Says yes. By the way, thank you so much, Christopher, for your participation and for your being here. That goes for everybody who's currently watching the stream and anybody who clicks on this video later on. Thank you for your time and attention. So yes, Chris was correct. The answer is yes. Water can act as both an acid and a base at the same time. And so that's what the autoionization of water refers to. It refers to water acting as an acid and a base at the same time. One water molecule donating a proton to another water molecule, which of course accepts it, right? So what does that look like? Well, the autoionization of water can be represented with this chemical equation here, where we have water plus water yields hydronium ion and hydroxide ion. So again, this equation just represents one water molecule that has donated a proton to another water molecule, and hydronium and hydroxide are what would be the result of that process occurring. And so just like in the example of a weak acid, we can write an expression for an equilibrium constant associated with this reaction. Now the expression is going to be very simple. Again, equilibrium, that's products over reactants. In this case, both of our reactants are pure liquid, so they will be omitted from the equilibrium constant expression. And so therefore, the equilibrium constant, which is called K sub W, it's also called the ion product constant for water, is going to be equal to the concentration of hydronium ion multiplied by the concentration of hydroxide ion. So Kw, ion product constant for water, it's simply equal to the concentration of hydronium times the concentration of hydroxide. So any sample of water, this is going to be happening. Now, it's not going to be happening this autoionization process, it's not going to be happening to a very, very large degree. Going to be very, very small, but nonetheless, it's something that's very, very important to understand. And so just to put a number on this, if you have a sample of water at 25 degrees Celsius, then your Kw, your ion product constant for water, is going to be 1.0 times 10 to the minus 14. Kw is 1.0 times 10 to the minus 14 at 25 degrees Celsius. In other words, the product of the concentration of hydronium ion and hydroxide ion at 25 degrees Celsius is 1 times 10 to the minus 14. That's a very, very, very small number. Now, it's at this point that I would like to take this to the whiteboard and see if we can derive some relationships. Now that we have this knowledge, let's see if we can derive some relationships about the relationship between concentration of hydronium, concentration of hydroxide, and this Kw, this 1.0 times 10 to the minus 14. So if you guys will just bear with me for just a moment, I am going to grab this information and just paste it into the whiteboard real quick. By the way, to those of you who are still watching, thank you very much for your being here. I wholeheartedly appreciate it. By the way, as I mentioned before, if you find value in this stream, I would definitely appreciate your giving it a thumbs up. And if, like I said before, if you're feeling super generous, consider sending a super chat. For those of you who don't know what super chats are, it's basically just a chat message that you attach to a monetary donation that stays pinned to the top of the chat window for a duration that is proportional to the amount of money donated. So the more money you donate, the longer your pinned chat message stays at the top. All right, so we're going to see if we can derive some relationships to understand this concept of the ion product constant for water and the autoionization of water. Let's see if we can understand this a little bit better. Well, we know that because water is the only source of hydronium and hydroxide, that means that the concentration of hydronium ion, H3O plus, is going to be equal to the concentration of hydroxide ion, OH minus, right? And since the product of these two is equal to 1.0 times 10 to the minus 14, that means the concentration of hydroxide, which is equal to the concentration of hydronium, is going to be equal to the square root of Kw, the square root of 1.0 times 10 to the minus 14. So because these two are equal, when you multiply them together, you get Kw. That means to solve for either one of them, you take the square root of Kw, which in this case is 1.0 times 10 to the minus 14. And again, this is assuming that we are at 25 degrees Celsius, the most commonly reported temperature in general chemistry textbooks, right? And so that means that this value is going to be equal to 1.0 times 10 to the minus 7, right? So that means that if you have a sample of water at 25 degrees C, that means that your concentration of hydronium and your concentration of hydroxide are both going to be 1.0 times 10 to the minus 7. That's a very, very small number. So only a very, very small portion of the water molecules have undergone autoionization. Most of them are, vast majority of them are still intact H2O molecules, but a small portion of them have reacted to form H3O plus and OH minus. So let's talk about what happens when we have an acidic solution and what happens when we have a basic solution. So let's say if we have an acidic solution, so I'm going to write this down real quick, acidic solution, right? Now, if we have an acidic solution, what does that mean? Well, that means that the concentration of H3O plus is going to go up, right? Concentration of H3O plus is going to go up. Now, in order for the concentration of H3O plus to go up, that means that the concentration of OH minus needs to go down. And the reason why anytime the H3O plus concentration goes up, the OH minus concentration needs to go down is because the product of these two is always going to be equal to Kw, which again, at 25 degrees Celsius is 1.0 times 10 to the minus 14, right? So again, if you have an acidic solution, you throw some acid in there, that means it's going to produce more hydronium ions, more H3O pluses. And in order for the product of H3O plus and OH minus to be 1.0 times 10 to the minus 14, the hydroxide ion concentration, the OH minus concentration, has no choice but to go down. And so if we look at, let's say if we have the opposite, let's say if we have a basic solution, right? Basic solution. Well, what that means is that your hydroxide ion concentration, OH minus concentration, that's going to go up, right? And again, the product of concentration of H3O plus and concentration of OH minus, the product is always going to be equal to Kw. And so the only way that that equation can still be valid is if your hydronium ion concentration goes down, right? And so I'm going to erase some of this stuff just so that we can get more of like a numerical, mathematical understanding of it. So I'm going to erase that, and then let's erase some of this. Need to grab my pen. Let's see. There we go. That's how I erase it. I have to use my pen to erase stuff. Go figure. Okay. So this is the relationship, right? I'm going to just leave that pinned to the top up there, right? So let's say that I have a sample of water, right? And I add some acid to it, right? So if I add some acid to the water, now that means that previously the concentration of hydronium ion used to be 1.0 times 10 to the minus 7. But let's say I add so much water that the hydronium ion concentration, the concentration of H3O plus, is equal to 1.0 times 10 to the minus 3, right? So again, I have some water. Originally, it was 1.0 times 10 to the minus 7. I added some acid in there. Now, all of a sudden, my H3O plus concentration is 1.0 times 10 to the minus 3. Could we figure out what the OH minus concentration is, knowing what we know about the autoionization of water? The answer is yes, because remember, the product, and let's see if I can do this. I'll just do it in black. I'll do it in blue. Remember, the product of H3O plus and OH minus is going to be equal to Kw, right? And at 25 degrees Celsius, that turns out to be 1.0 times 10 to the minus 14, right? And so we can set this up sort of like as an algebraic equation, right? We know that the concentration of hydronium ion times the concentration of OH minus is going to be equal to, and I'm just going to move this aside to give myself some room here. There we go. 1.0 times 10 to the negative 3 times the hydroxide ion concentration is going to be 1.0 times 10 to the minus 14. And so all we need to do to solve for the hydroxide ion concentration in this case is to divide both sides of this equation by this 1.0 times 10 to the minus 3. And in so doing, we get 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 3, which in this case would be, erase that to avoid the confusion. In this case, it would end up being 1.0 times 10 to the minus 11. So just to recap, I'm talking about what happens when you add acid to water. When you add acid to water, your hydronium ion concentration of H3O plus goes up, and simultaneously the hydroxide ion concentration goes down, such that the product of the concentration of hydronium and hydroxide is equal to the ion product constant for water, Kw, which is at 25 degrees Celsius, 1.0 times 10 to the minus 14. Okay, that was kind of a mouthful, but I hope that sort of helps understand acids and bases a little bit more. And in the live streams and videos that follow, we're going to talk about the most commonly used scale that is used to easily quantify acids and bases, acidity and basicity. It's called the pH scale. Unless you've been living under a rock, I'm sure you've heard of it before. So, but for now, that is pretty much all we have for today. That's going to wrap up the show. Thank you guys so much for watching. I didn't get a lot of messages in the chat, and I got 0 super chats, but I really, really do appreciate you guys watching. Thank you very much for being here. As always, like I said, your feedback is absolutely necessary, very, very important for me to improve upon these live streams. I think I'm starting to get a little bit more of a hang of it, but I don't know. I'm not the judge of that. You, the audience, are the judge of that, and therefore I would be delighted to hear any feedback you have to give, whether that's in the chat or calling in via Discord or sending me an email. I mean, there's just so many ways by which you can get in contact with me. There's Facebook, there's Instagram, there's Twitter, all that stuff. If you're interested, you can get in contact with me if you like. But that's going to do it for me tonight. So I hope you guys have had an excellent weekend, and I hope you are geared up to have an awesome, great, safe, productive week. Go out there and kick some butt. All right. Thanks, guys. Talk to you later. Bye.